Let's discuss about nuclear fusion. Fusion literally means the fuse of two or more things to form a single thing, or maybe more than that. Now, nuclear fusion is actually a very large source of energy, like what we get from the sun, and it also has a lower impact on the environment. Let's see how it happens. Suppose there are two lighter nuclei, they fuse to each other with a larger one, and we get some energy because of this reaction. This energy is the outcome of this reaction. Let's have a look at the binding energy graph. Binding energy per nucleon with the number of atomic mass. So here is the hydrogen, and at the extreme point there is uranium. Hydrogen has the most amount of binding energy. Helium is slightly lower in binding energy. So if we fuse two hydrogen, as in the case of sun, some amount of energy is released to form the helium. This is actually to visualize that when uranium is transformed into iron, that means when it is going towards the left side, that means its binding energy increased and energy level becomes lowest, and lowest energy level is the ground state, and lowest energy level is the most desired thing by nature. So the highest binding energy is actually referred to the lowest energy levels. Binding energy of a proton, if we can consider a hydrogen atom, then a hydrogen contains one proton and one neutron. And binding energy of hydrogen, as we can see, and I have mentioned that binding energy of hydrogen is greater than helium. So here there is a shift from this point to this point when hydrogen becomes helium. But in case of sun, there is a huge temperature residing within the atmosphere of the sun. So in case of sun, there are plenty of hydrogen, but they are very hot, and what they form is called the plasma. What is a plasma? Grossly we can say that at very high temperature, the electrons from the atoms are stripped from the grasp of protons. So electrons are no longer bound to the nucleus then. Though plasma is itself a neutral kind of thing, we actually get a soup of charged particles. For example, in case of hydrogen, in very high temperature, as in case of sun, the electrons manage to escape from the grasp of protons, and we get a soup of protons and electrons, that is positive charge and negative charge, because the hydrogen is a combination of proton and electron. There is no neutron inside the hydrogen nucleus. So we get, in case of plasma in sun, we get protons and electrons. And in sun there are lots of protons which will be used, which is used by the sun to get an enormous amount of energy, and for which the sun is shining for 5 billion years, and it will shine for another 5 billion. What happens to a proton inside the sun is, first a proton becomes a neutron which is neutrally charged, which has no charge, it emits a positron, which is just an electron but positively charged. And we get neutrinos. These are very tiny particles, very tiny mass, and they are everywhere. They can pass through anywhere. They can go through you. They can go through any object in the universe. They often comes from the atmosphere, higher atmosphere, that is from the cosmos, to our world. Now let's have a reaction that there are plenty of protons inside the sun. So one proton has become a neutron, so we have one neutron, and this neutron is meeting up another proton inside the sun. What we will get is a deuteron, and deuteron is basically a combination of neutron and proton. In deuteron there is one neutron and one proton. So it can be written as, this is for one proton, this is for one neutron plus one proton. Now this deuteron will again combine to the proton and it will make a helium-3. Helium-3 is 2 protons and 1 neutrons. Then this helium-3 meet up another helium-3 which produces a helium-2-4, which contains 2 protons, 2 neutrons, and we get 2 protons also. And in all these steps of reactions we get huge amount of energy release, and this is what is exactly happening inside the sun. Now how the protons come together, because protons are positively charged, whenever they try to come to each other there will be a Coulomb repulsion. If we want to fuse them, that is, if we want to make the nuclear attractive force to act between them, we need to sufficiently make them closer so that the nuclear attractive force comes into play. So if we want to bind the protons, a huge amount of energy is needed. And the huge amount is, as a statistics we can give that it is 1 million electron volt per nucleon. This much of energy is needed for binding of 2 protons, unless we can't come across the Coulomb repulsion between the protons. And 1 electron volt is 10 to the power 4 Kelvin in terms of temperature, if we can say. So 1 million electron volt is 10 to the power 10 K, 10 to the power 10 Kelvin, and this is a really hot kind of thing, because 10 to the power 10 K is 10 billion Kelvin, and this is the temperature of the sun. If we have a look at the number of nucleons with the energy, this is the energy distribution curve of the nucleons, that is how the number of nucleons vary with energy. We get maximum number of nucleons will have 1 million electron volt of energy, which will again producing 10 billion Kelvin of temperature. This is the